Bismillah ar-Rahman ar-Rahim. Okay, in previous talks, we defined what we mean by power series. If you remember, we said a power series is a series that has the form summation of n equal to 0 up to infinity, that is Cn times x minus a to the power n, and we said this power series is said to be centered at a. We studied how to find the radius of convergence and interval of convergence. These are the points x such that this series makes sense. Then we ask the question, if we are given a function f of x, can we represent this by a power series? And we answered the question partially. We said if we have functions like, for example, 1 minus x, that was the basic point we used, that is using the geometric series test, then this is equal to n equal to 0 up to infinity, like x to the n, and we know that this is making sense only if absolute value of x is less than 1. Some modifications of this kind of functions can be reformed as 1 over 1 minus x, then we can represent them in terms of power series using what we call geometric series test. The next question is, if we are given any function f of x, okay, how to represent it as a power series? We have actually two interesting problems. The first one is, which functions have power series representation? So what kind of functions are qualified to have power series representation? That's the first. Second one, how can we find such a representation? We will concentrate in the second one, how to represent a function in terms of a power series if it has a power series. And this is what we call Taylor and Maclaurin series. So what is the theorem here? It says, if you have if this function, we assume from the beginning that it has a power series representation. That is, we can rewrite f of x as a power series. Now we need to specify what are the Cn's. Now, Taylor says, then you can find the Cn by the formula here, which is finding the nth derivative at a divided by n factorial. Now, a special case of this series is called the Taylor series of the function f of x, centered at a or about a. If you specify a to be 0, you will have the special case, which is f to the n of 0 over n factorial. F to the n at 0 over n factorial multiplied by x to the n, and this is called the Maclaurin series of the function f of x. Now, before we go and apply this theorem now to find power series representations of a given function, then we use them as an application on some problems. Let me say something about the proof of this theorem, or how it moves, why we got here Cn equal to f to the n at a over n factorial. And it is very simple here. This is the idea of the proof. The idea of the proof is so simple here. Just the only thing we need to go back, because we assume now that we have a power series representation for f of x. It means you can expand f of x like this. You can rewrite it as what? It is C0 plus C1 times x minus a plus C2 times x minus a all squared plus, let us move one more, C3 x minus a to the power 3 plus etc. C4 x minus a to the power 4 plus this will go indefinitely. Okay, fine. What we are trying to do here is to figure out what are the coefficients. These are called the coefficients, Cn's. So we need to figure out what is C0, what is C1, what is C2, what is C3. That's the idea here. So how to get these values, C0, C1, C2, C3, C4? Simply you can see now, if we substitute a in both sides of the equation here, all these terms involving x minus a will be zeros. So what do we have? We have C0 actually is nothing but f of a. I am substituting in that equation by a for x. So x equal to a minus a will be 0, this is 0, etc. So we have C0 equal to f of a. Fine. Let us move and find the derivative here. Okay, we have the derivative of the function f of x. If we differentiate, this will disappear. It will be 0 because this constant, the derivative constant will be 0. Then I have here C1 plus, that is 1 times 2 C2 times x minus a to the power 1. Plus, this will be 3 times C3 times x minus a all squared plus 4 C4 times x minus a all to the power 3 plus etc. Okay, fine. Observing again that if we substitute a here, then all terms after the first term will be zeros. So what do we have? We will have C1 is equal to f prime at a divided by 1. Actually, it is 1 times C1. Or we can write it 1 factorial. I'm trying to generalize the formula. So we need to do some calculations and see what is the scheme here. How to find out the nth derivative or how to find the Cn in general. Okay, let us do more calculation here. Let us find, for example, the second derivative and observe what's happening here. The second derivative, the first term also is constant in the f prime, so it will disappear. Then what do we have here is just 1 times 2 times C2 plus. The next item here is, it will be 1 times 2 times 3 times C3x minus a. That is to the power 2, so it will be to the power 1. Plus, that is 3 times 4 times x minus a to the power 2 plus, etc. Again, observe that if you substitute a, then f double prime of a, okay, everything here will be 0. If you divide by 1 times 2, which is 2 factorial, you will get what? C2. So C2 is nothing but the second derivative at a divided by 2 factorial. Let us do one more. Okay, finding the third derivative now. If you find the third derivative at x, this is equal to. Finding the third derivative, it means this will be 0 again. And what do we have here is just 1 times 2 times C3 plus, for the next one here, it will be 1 times 2 times 3 times 4 times x minus a plus all these terms involving a. Find out now C3. What is C3? It is nothing but substituting a in both sides of the equation. Everything here will be 0. What we have is f triple prime at a, divide by 1 times 2 times 3, that is 3 factorial. Move with the same way, just do some differentiation process and substitute. You will find out now the scheme is like this. You see, C1 is f prime of a over 1 factorial. C2 is f double prime of a over 2 factorial. C3 is f triple prime of a over 3 factorial. So Cn will be what? It will be nth derivative of a divided by n factorial as it is written in the formula here. Now, this is what we call the derivation of the formula, which is called the Taylor expansion. As a special case, if you have a equal to 0, then it's called Maclaurin series. What we need to do next is to apply this to find power series representation of some well-known functions like the e to the x, sine of x, cosine of x, etc. That will be done in the next point. Okay, let us see now how to use this nice theorem to represent some functions in terms of power series. For example, we start with this well-known function, the exponential function. We have f of x equal to e to the x. We need to represent it as a power series, as a Maclaurin series. We need to find its Maclaurin series representation. And then we need to say something about its radius of convergence. The second part, we need to use it to find the exact sum of the following series. Okay, so let us start the process here. I have f of x by formula. It's equal to, by the Maclaurin series says, then this is equal to n equal to 0 up to infinity. It is the nth derivative of the function at 0, evaluated as 0, divided by n factorial. Then it is multiplied by x to the power n. That is the formula we have. So what is the challenge now? The challenge is to just calculate the nth derivative at 0. So how to find the nth derivative of the function? We start with the function itself, f of x, which is e to the x, and observing that differentiating the exponential function will give the same function. So all the way, we need to move up to the nth derivative of x. For the exponential function, it will be e to the x. Evaluating each at 0, then this will be e to the power 0, which is 1, e to the power 0, that is 1, e to the power 0, which is equal to 1. So this implies that the e to the x function is equal to summation, which is n equal to 0 up to infinity, and then the evaluation at 0 for any derivative is equal to 1. So at the end of the day, we end up with x to the power n divided by n factorial, and someone can show that this is convergent for all values of x. So I will write it directly by using the ratio test. You can show that the radius of convergence here is infinity, meaning You can go everywhere from 0. I mean, it is convergent for any values of x, any real number x. So this is the exponential function. It is presented by this. If you just look at it in the expand form, it means e to the x is nothing but 1 plus what? X plus x squared over 2 factorial plus etc. x cubed over 3 factorial and so on. You have it up to x to the n over n factorial, and you move like this. Okay, fine. That's the first part. We calculated the derivative, we substituted, we got what we call the Maclaurin series for the exponential function. The second part here is as application of this. It says, find the exact sum of this expression here, which is 1 plus ln of 2 plus ln of 2 all square over 2 factorial, and this will move in the same way. So what is the final answer? Okay, if you remember in series, we did two kinds of series where we were able to find the exact sum. The geometric series as well as the telescoping series. Not anything else. Now we will add one more, that is a special case of Maclaurin series and Taylor series. What I mean by a special case, when you go to the representation here, and you know it is convergent for any values of x. So it means you can always substitute a value for x here, and it will give you the same answer if you substitute the same value in the left-hand side. Comparing this with the question here, it seems that our x, which is already substituted in the expression of the Maclaurin series, is just ln of 2. Because you can match this with the right-hand side, you will find that always we have ln of 2, ln of 2, ln of 2. So it means that 1 plus, so this is part B, 1 plus ln of 2, okay, plus ln of 2 all squared over 2 factorial. This is squared over 2 factorial plus etc. like this. This is nothing but it is the exponential function evaluated at ln of 2. And you know the answer here is equal to what? Equal to 2, because these are inverse of each other, and then you have the answer is equal to 2. Okay. We will do the same now for other types of functions. We did for exponential function. Let's take another exercise. I will say, do the same, meaning find the Maclaurin again series for, let us say, start with the sine function, for example, 5f of x equal to, let us take the sine function, sine of x. Okay, find the Maclaurin series for the sine function, and we need to state, of course, the radius of convergence again. Because always when we deal with series, we need to have a restriction in the series. One, it is convergent, one, it is divergent. Procedure will be the same. We have a formula for this. We need to find the series representation as a Maclaurin series. So the center is 0. It means the series has the following shape. It's n equal to 0 up to infinity. And that is the nth derivative of the function at 0 divided by n factorial multiplied by x to the power n. That's what we need to find. So the challenge here is again to find the derivatives of the sequence of derivatives of the function. Okay, fine. Let us calculate this. F of x is equal to sine of x. Okay. The first derivative of the function f prime of x will be just cosine of x. Fine. The second derivative of the function at x will be equal to minus sine of x. Look for the third derivative. The third derivative of the function at x will be equal to minus cosine of x. But the fourth derivative of the function, if you say 1, 2, 3, 4 of x, this is equal to again sine of x. So what does it mean here? It seems that we have a cycle of order 4. Look, each 4 derivatives will go back to the same. 1, 2, 3, 4, come back to the sine. Next one will be cosine, next will be minus sine, next will be minus cosine, then come back to the sine. So it is a cycle of order 4. So we have a sequence of derivatives where they repeat themselves after each 4 items, each 4 iterations. Okay, so that's what we have. Fine, what we are trying to do here is to evaluate these at 0. So let us find, for example, the expansion here, sine of x, if you just look at it from another angle here. Sine of x is nothing but, actually it is f of 0, which is sine of 0 in other words. If we call f of x equal to the sine, let me say like this. F of x is equal to sine of x, if you need to expand it in Maclaurin series, you are trying to find actually f of 0 plus f prime at 0 divided by 1 factorial times x plus f double prime of 0 divided by 2 factorial. This is x square. I'm just rewriting this compact form in an expand form only, just to observe something here. F triple prime at 0 divided by 3 factorial times x cubed, and so on. You move like this. If the fourth derivative at 0 divided by 4 factorial, x to the power 4, let me add one more, the fifth derivative of the function at 0 divided by 5 factorial, x to the power 5 plus, etc. But observe now the following. If we substitute at 0, f of 0 will be what? It will be 0. So this is exactly equal to 0. What about f prime of 0? Okay, this implies f of 0 equal to 0. So we have no constant term. The constant term will disappear. This implies f prime at 0 is equal to 1. Okay? If double prime of 0 again is equal to 0. If double prime of 0 equal to 0, it means this term also will disappear. It will be 0. The third derivative here at 0, this implies the third derivative at 0 is equal to what? Minus 1. The fourth derivative at 0 is the same as the function at 0, the evaluation of the function at 0. So for the fourth derivative at 0 again is equal to 0. So what's going on here? It seems that all even terms will go to 0. It will be exactly equal to 0. So which terms will survive here? Only the odd number of terms. The odd number of terms. So what do we have here for the odd number of terms? We will have something like this. 1 minus 1, 1 minus 1. So for the first derivative, it is 1. Third derivative, minus 1. Fifth derivative, 1 again. And so on. The seventh derivative will be minus 1. So it is alternating in sign. So sometimes it is 1. The other time is minus 1. The third time will be 1. The fourth time will be minus 1. So what is the end of the calculation here? It says sine of x, it seems to be involving only the odd number term, So this is n equal to 0 up to infinity. I need to express it as alternating minus 1 to the power n. Why minus 1 to the power n? Because I start with the positive one, starting from 0, positive, negative, positive, negative, positive, negative. But the exponents of x only having what? Odd numbers. So it is just 2n plus 1 divided by, okay, we have divided by n factorial. For the odd terms, it will collapse, but for the, for the even terms, everything will be 0, but for the odd terms, we have here 2n plus 1 factorial. That's exactly what we call the Maclaurin series for the sine function, together with the radius of convergence. Again, by using the ratio test, someone can show that this is convergent for any x. So again, I will write here the radius of convergence is equal to infinity, indicating that this series is convergent for all values of x. Okay. What can we gain from this? Two beautiful things we can do. We can obtain two things from here. The first one, as a result, I will say, as a result of this, we have the following. We have the following. Okay. We can get the cosine representation. Why? Because what is the derivative of the sine? The cosine. The derivative of the sine is the cosine, and we had a nice theorem that says, if you are inside the radius of convergence, then always you can differentiate term by term. If you do that, then we will have the Maclaurin series for the cosine function. What is the Maclaurin series of the cosine function? It is the derivative of this. It is the derivative of this. So it is the derivative d by dx of the sine function, sine of x. And what is the derivative? If you just do the simplification here, you will end up with n equal to 0 up to infinity, and then you have minus 1 to the power n, x to the power 2n divided by 2n factorial. Okay, how to obtain this? If we differentiate term by term, what's happening here? This will be 2n plus 1 downstairs, right? Okay, forget about minus 1 to the n. This is constant. I'm differentiating with respect to x. So that will give me 2n plus 1 multiplied by x to the power. I subtract 1 from this. So I will have 2n here divided by 2n plus 1 factorial. What is 2n plus 1 factorial? It is 2n plus 1 multiplied by 2n factorial. Now 2n plus 1 will cancel with 2n plus 1, and I end up with x to the power 2n divided by 2n factorial. This is one thing we can gain from this result, which is for the sign. And you remember that the theorem says if the radius of convergence is infinite here, also the radius of convergence will be infinite here. Differentiating or integrating a power series do not affect what? Do not affect the radius of convergence. That's one thing we can gain. A second point we can gain from here, I can write it as an exercise. I can write it as an exercise, says, find, now always this will be gained directly after solving any representation of functions by power series. We can gain some special cases. For example, find the exact value of, and I will just write something like this. It is just n equal to 0 up to infinity. That is minus 1 to the n, for instance here. I can write here pi to the power 2n plus 1 all over. That is 6 to the power 2n plus 1, okay, multiplied by 2n plus 1 factorial. What is the exact answer for this? What is the exact sum for this? Of course, this is not one of the geometric series or telescoping series we did. It is something different here. It is not straightforward to get the answer unless you figure out this, or you just consider this one as a special case of the representation we have here for the sine. You can see it is similar to the sine function here, okay? And then you just try to figure out what is the value of x substituted here. And clearly, if you just reform it like the standard form we have for the Maclaurin series of the sine, then you have n equal to 0 up to infinity, and that is minus 1 to the power n. I will write it down as pi over 6 all to the power 2n plus 1 all over 2n plus 1 factorial. Meaning, I'm going back to the sine representation here in terms of series. I'm choosing a specific value for x, which is inside the interval region of convergence, sorry. I'm choosing x here to be inside the region of convergence. And in that case, specifically, I choose the x to be pi over 6. So what does it mean? It means that this series is nothing but the sine function evaluated at pi over 6. And you know what is the sine of pi over 6? Sine 30 degrees is equal to 1/2. So it means when you add all these terms, the infinite terms, the final answer will be 1/2. So we succeeded now to do the Maclaurin series for e to the x. We have also for the sine function. We have also for the cosine function. Not only this, we can do more. Okay, let us use the benefit of the discussion we made to represent other types of functions. For example, let us do more exercises about representing a function by power series or representing different types of functions by power series. So I will do more exercises in this regard that says find, let us say find the Maclaurin series of the following functions. So let me say part A, I will take f of x to be equal to x cubed e to the power 2x. Okay? This is the first part, then I will add a second part. Okay. It's not always we need to go by definition to find the answer. Because you know the challenge in the definition is to find the nth derivative, which is not always straightforward. Sometimes you need to get the benefit of the results we gain in order to find new results also. How to find the representation of this as a Maclaurin series? I start with always the very basic one, e to the power x. And what is e to the power x? We just derived this. It seems to be n equal to 0 up to infinity. That is x to the power n divided by n factorial. That's what we have for e to the x. So what do we need to do? We need to move now to e to the power 2x. Okay, e to the power 2x. So what we are doing here, we are just replacing x by 2x. Replacing x by 2x, what do we have here is just 2x all to the power n divided by n factorial, which is actually equal to the summation of n equal to 0 up to infinity, and that is 2 to the power n, x to the power n, divided by how much? N factorial. Okay, we reach up to e to the power 2x. Now, multiplying by x cubed. So this implies x cubed e to the power 2x can be written as summation of n equal to 0 up to infinity, and that is just, okay, it is 2 to the power n, x to the power n plus 3, that is just adding 3 to the exponent, divided by n factorial. Again, this is convergent for all values of x. You can check this by using the ratio test that the radius of convergence here, r, is again infinite. Okay, so we have convergence for all values of x. This is another example of how to represent a function by its Maclaurin series. Okay, next we will see how to represent different functions in terms of Taylor expansion. Okay, that will be our next point. Okay, before we see how to represent a function by Taylor series, let us add one more part here as we promised. So, how to represent x sine x cubed now? X sine x cubed, the only thing you need to do is to start with the very basic function that is sine of x. And you know sine of x, we derive this to be the summation n equal to 0 up to infinity, that is minus 1 to the power n, x to the power 2n plus 1 divided by 2n plus 1 factorial, and we observe that this involves only odd powers of x, and that is not amazing because this is an odd function actually, and so it is matching with the behavior of the sine function. Anyhow, we are trying to represent x sine x cubed in terms of a power series. I say instead of doing it from scratch here, going back to find the derivative, second derivative, third derivative, nth derivative, which seems not to be easy, we need to use the results we had. That's why it is recommended always to remember the representation of e to the x, the representation of the sine of x, the representation of the cosine, tangent, inverse. These are the basic functions we did before and we will do soon. Okay, fine. So, how to find the representation now of x sine x cubed? The only thing I need to do is to substitute for x by x cubed. I replace x by x cubed. So, what do we have? We get the following. N equal to 0 up to infinity. It is minus 1 to the power n. I will replace x by x cubed. So what do we have here is x cubed all to the power what? 2n plus 1. 2n plus 1 divided by 2n plus 1 factorial. Fine. Simplifying. So this will give n equal to 0 up to infinity, and that's minus 1 to the power n, x to the power 6n plus 3. 3 times 2, 3 times 1. All over, this is 2n plus 1 factorial. Fine. Last step. We have, this implies now, x sine of x cubed is equal to. We just multiply by x to have n equal to 0 up to infinity. And that is minus 1 to the power n, x to the power, this will be 6n plus 4, all divided by 2n plus 1 factorial. Of course, I need to put some parentheses here to indicate that 2n plus 1, all of it is inside the factorial. Okay, these are some samples of functions where we can represent them by power series, either by using the definition, either by using the definition or by using results obtained from the definition. Okay, fine. What about the Taylor expansion, Taylor series they call it, or the representation of f of x by power series centered at 2, or about 2, or centered at 2, the same. What should we do? I need to represent this f of x. I will use the theorem which is done by Tyler. It says, okay, if you need to find the power series representation centered at 2, the only thing you need to do is to calculate the nth derivative of that function at 2 divided by n factorial and then multiply by x minus a all to the power n. A here specifically is equal to 2, so x minus 2 all to the power n. That is the answer. The only thing we need to do here is to search for what is the nth derivative of that function at 2. And you see this is very nice function. We know that its nth derivative of x is always e to the power x. So this implies, of course this can be done by just finding sequence of derivative and observing that the derivative is not changing here. It's always e to the x. So what is the nth derivative of the function at 2? It's equal to e squared. All the time it's e squared. Substituting back here, we have e to the x is represented by the Taylor series n equal to 0 up to infinity. I'm substituting for this value by e squared. So this is e squared divided by n factorial, and that is x minus 2 all to the power n. And again, you can show that this is, convergent for all values of x. This is convergent for all values of x. The radius of convergence here is infinite just by applying the ratio test. The ratio test will give that this is convergent for all values of x. Okay, let us do it for the sine function now. Find the Taylor series expansion of f of x. I will change the function e to the x into the sine function, and I will change a to be pi over 3. Let us see what kind of series will be obtained now for the sine function if we are shooting for representing the sine in terms of a certain Taylor series centered at a given point. Okay, the sine cosine functions, they have nice behavior of their derivatives. They move in cycle, okay, of order 4 as we observed before. Let's do the same here. Let's call this one, okay, exercise again. Find, I will say find, this is find the Taylor series of, let us choose the sine function for instance, f of x equal to, just to see how to apply this formula, sine of x at a equal to pi over 3, okay? We are trying to find the power series representation. Specifically here it's called Taylor series, centered at a equal to pi over 3. Okay, fine. We know how to find it out by using the theorem. The only thing we need to search for is a formula for the derivatives of the function. So looking for derivatives of this function here, I will get this. I have f prime of x is, again, is what? This is equal to cosine of x, derivative of the sine function. So this implies f prime at pi over 3, if you like, this is equal to, substituting here, this will give you 1/2, okay? Of course, let me just make some space here. I will say at of this function, okay, at x equal to pi over 3, I can now erase this to make some space downstairs. So I will say f of x equal to, I need to add this line because we need to evaluate the function at pi over 3. So this is f of pi over 3, and this is equal to what? Sine pi over 3. Sine pi over 3 is just radically 3 over 2. Okay, let me repeat my calculation now. F prime of x will be just equal to the derivative of sine, that is cosine of x, and this will give f prime at pi over 3 is nothing but 1 over 2. Okay, cosine pi over 3, which is 1/2. Fine. We need to do some derivatives, more derivatives here. Second derivative will be minus sine of x, and this will give minus sine x, means the second derivative at that point, pi over 3, which is a in this case, is equal to minus radically 3 over 2. Fine. Third derivative, we said, third derivative of the function will be just minus cosine of x, and evaluating the third derivative at pi over 3, again, will give what? cosine pi over 3, which is 1/2. So this is minus 1/2. Finally, we just reached the last one here, the fourth derivative, because all others will be just repetition of this. So this is the fourth derivative of x, which is equal to, this is x. So fourth derivative of x will be just the sine of x. So we are back to the same original function we have, the sine function. So what we are expecting now, that all other values, this is the fourth derivative at pi over 3, is again to be equal to, substituting here, this will be radical 3 over 2. Let us stop here and try to observe something here. I can see all even terms. This is the zero derivative, constant term. Okay, second derivative, fourth derivative. They involve, coefficients like radical 3 over 2, radical 3 over 2, radical 3 over 2. But it's sometimes plus, sometimes minus, plus, minus, plus. The next one will be minus, plus, minus. And the odd number terms, the odd powers of x, f prime, f double prime, f prime, f triple prime, always we have here 1/2. The third derivative will be minus 1/2. So the fifth derivative will be 1/2. The seventh derivative will be minus 1/2. So it's like 1/2 minus 1/2, 1/2 minus 1/2. So it means the nth derivative here, we have two behaviors. One for the odd powers and one for the even powers. So what I will do here, I'll go back to the Taylor series and I will split it into two series. One of them involving the even terms and the other one involving the odd terms. Then I will add them together to find the answer. So what I will do here, I know that the sine function, which is f of x, is equal to summation of n equal to 0 up to infinity by the formula we had, which is Taylor, says it is the nth derivative of that function evaluated at pi over 3. Of course, you need to divide by n factorial, and then you multiply by x minus pi over 3 all to the power n. That's the formula we have. But by calculations we did here, we found out that we have two behaviors of the nth derivative. For the even terms, we have one behavior. For the even terms, we have radical 3 over 2, radical 3 over 2, radical 3 over 3, but alternating in sign. For the odd terms, we have 1/2, 1/2, 1/2, but alternating in sign. So meaning, I can always rewrite this. It's always possible to rewrite this one as n equal to 0, okay, up to infinity. I will take first the even terms. So f2n of pi over 3, okay, over, I will take only the even term, so it is 2n factorial. Just taking n to be even, so I will choose it to be this way, 2n, that is this will involve all even powers of x minus pi over 3. Plus, I will add now the odd terms, n equal to 0 up to infinity, that is f2n plus 1 at pi over 3, that is what we have here, divided by 2n plus 1 factorial, okay, and this is multiplied by x minus pi over 3 all to the power 2n plus 1. Okay, fine. Now let us borrow these values and substitute to get the final answer. So this is equal to, substituting for the even terms, these are the even terms, we have always radical 3 over 2 with a minus sign alternating. So this is n equal to 0 up to infinity. This is minus 1 to the power n. And that is always radical 3 over 2, radical 3 over 2, divided by, we have here, what? 2n factorial, this is inside here, multiplied by x minus pi over 3, all to the power 2n plus 1. That's the first one. Plus, the second series will involve the odd powers, n equal to 0 up to infinity. Again, it is minus 1 to the power n, but the value is always 1/2 here, all over 2n plus 1 factorial inside like this, and this is x minus pi over 3 all to the power 2n plus 1. That's it. Again, this series is convergent for all x. So this is the way we can present a given function by a power series, and the challenge here always will be how to find the general form of the derivative, the nth derivative of the function. Most of the time we ask only about finding few terms of the series, because in order, if the series is convergent, the more significant terms will be the first few terms, okay? So practically we just find like 5 terms, 6 terms, 7 terms, something like this. It depends on the error we are shooting for, but usually we ask for the Taylor series for a few terms, but if you need to find it in general, the challenge always will be to find the nth derivative at a point. That's called the Taylor series representation of a given function. Okay, so we saw some examples now how to do the Maclaurin series, how to do the Taylor series. Let us see some application for this. More applications for these representations. That will be done now. Okay, now let us see some applications. For example, here the question says, evaluate the integral of e to the power minus x squared dx as an infinite series. Of course, this kind of functions, e to the power minus x squared, e to the power x squared, we don't have a closed form for their integrals. I mean, these are not elementary functions. So an alternative way to evaluate the integral is to move and integrate in terms of power series. So what should we do? First, we need to find the representation of e to the power minus x squared as a power series. Then we just integrate as what we did before. Okay, so what is e to the power minus x squared? I come to e to the power minus x squared to rewrite it as, this is n equal to 0 up to infinity. You remember we have e to the x. E to the x is just n equal to 0 up to infinity. That is x to the power n over n factorial. This is what we derived. So the only thing we just replace x by minus x squared, and we have minus 1 to the power n, that is minus to the power n, and this will give me x to the power 2n, of course, divided by n factorial. What I did here, I just replaced x by minus x squared in the derivation of e to the x as a power series or as Maclaurin series, as we said. Okay, fine. What we are trying to do is just to integrate. So what I will do here, integrating e to the power minus x squared dx, and you know that integrating a power series is possible if we have the interval of convergence. If we are working in the radius of convergence, in the interval of convergence, then we can go inside and integrate term by term as what we did before. Okay. This series is convergent for any x, actually. This is the radius of convergence here, again, is infinite. So we can integrate term by term to get the following. N equal to 0 up to infinity. That will be minus 1 to the power n. We are integrating a power series like what we are doing with polynomials. We just add 1 to the exponent and divide by the new exponent. And that will give you n factorial multiplied by 2n plus 1. And don't forget to add also constant of integration plus c. So that is what we mean by finding the integral in terms of an infinite series or as a power series expansion or power series representation. Another example of interest here is to find this limit by using power series. Yes, I know that someone will say, why do we need power series? Because this can be evaluated by using Hopital's rule. For example, if I substitute 0 here, I will have 1 minus 0, that is 0 over 0. So it is one of the indeterminate form we have. And then I can differentiate maybe 2 times to get the answer. Okay, let us do that. By using Hopital's rule, you can show that the answer is differentiating. You get e to the x minus 1 over 2x. Again, this is 0 over 0 type. So by using Hopital's rule again, another time, this will give us the answer. Limit as x goes to 0. And that will be e to the x over 2. And the final answer after substituting, the answer will be 1/2. Yes. But we need to make sure now what we are doing now is fitting of what we have done before. So we will do it by using power series. Instead of doing it by Hopital's rule, this will give an alternative way to find the answer. How to do that? Okay, I have e to the x. I remember e to the x is what? Summation of x to the n over n factorial. That is 1 plus x squared over 2 factorial, which is 2. If you like 2 factorial here, plus x cubed over 3 factorial, plus x to the 4 over 4 factorial, and so on. Plus, up to infinity. Fine, this is e to the x. Let us subtract 1 and subtract x from both sides of this equation. So this implies e to the x minus 1 minus x is equal to, I'm taking 1, taking x to the other side, or subtracting 1 and x from both sides. That's what we are doing here. So this will give x squared over 2 plus, if you like, 2 factorial or 2, whatever. Okay, it's the same. X cubed over 3 factorial plus x to the 4 over 4 factorial plus blah, blah, blah. Okay, fine. Let us now divide by x squared and then take the limit. If we divide by x squared, this is what we have. E to the x minus 1 minus x divided by x squared will be equal to. Look here, if we divide by x squared, this will be only 1/2 or 1 over 2 factorial. Okay, let's leave it 1 over 2 factorial for the time being. Plus, that is x over 3 factorial. Plus, that is x squared over 4 factorial. And all other terms here will involve the value of the expression x, except the first one. Now, taking the limit of both sides, clearly we have limit as x goes to 0 of e to the x minus 1 minus x over x squared will be equal to. Taking x to go to 0, everything here will be 0 except the first term, that is equal to 1 over 2, and this result is matching with the result we gain by using Hopital's rule. So yes, what we are doing here for series representation of functions is fitting with what we have done before. It is adding more also, that we can now go to the option to find the integrals of some non-elementary functions in terms of power series. Okay, and that is practically is very nice because we can always find these integrals up to a certain accuracy we need. Okay, that is the application for Taylor series. We also did some applications by substituting special values for x in different type of Maclaurin series, and we get the exact sum of some infinite series. Fine. What is next? Now, if we are given a function, then by applying the rule we have for Taylor or Maclaurin series, we can find the representation by applying the definition. That is, finding simply the derivatives, f a prime, f double prime, nth derivative, etc. If you have product of two functions, if you have division of two functions, can we find the power series representation without going to the definition? Do we have product of two power series or division of two power series? This will be illustrated in the following exercise. Okay, let us see this nice exercise that says, of course, the title here is multiplication and division of power series. So the question says, find the first three non-zero terms in the Maclaurin series of, and this is a given function. We call it f of x, whatever. E to the x times sine of x. We have two options here. We have the function f of x, which is defined to be e to the x multiplied by sine of x. So someone can go and search for the first three non-zero terms in the Maclaurin series by applying the definition that says f of x is f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared plus etc. And he needs to continue until he reaches three non-zero terms, because here, for example, clearly f of 0 is 0. So we are not looking for this term. Next term, you need to find the derivative. Next term, you need to find the second derivative. Next term, you need to find the third derivative, and etc. I'm trying to do the same without going through the definition. I will use my background or my results again from the definition for the basic functions e to the x sine x to derive the Maclaurin series of the multiplication. So what I will do here, since I'm looking for a few terms, I will say e to the x sine x. What is the representation of e to the x? We did this. It is 1 plus what? Plus x squared over 2 factorial, which is 2 actually, plus x cubed over 3 factorial. 3 factorial is just 1 times 2 times 3, that is equal to 6 plus. Enough, because I'm looking only for the first three non-zero terms. Fine. What about sine x? Sine x is, again, it is well known for us. It is x minus x cubed over 3 factorial. 3 factorial is 1 times 2 times 3, that is equal to, okay, 6 plus, that is x to the power 5 over 5 factorial, which is 120, plus, etc. Okay, that is the second series we have. Okay, fine. If we need to do power series multiplication, it's exactly the same as what we have done for polynomials. We multiply and add exponents. That's it. So what you need to have here, and using the distribution law of multiplication. So I will look for the first term, for example. Here 1 times x will be what? Will be x. Let me see if there is another term that will give me x also. If I multiply 1 by this or 1 by the next one, it will never give us x. And if you multiply x by any term there, nothing will give you x. So the final answer is, I mean for the powers of 1, x to the power 1, we have only one term, which is 1 times x. Okay, what about the next one? X squared. 1 times any other term here will not give me x squared. The only thing that will give me x squared is either x constant by x squared. We don't have x squared here. X by x, that will give me x squared, or x squared by constant. Okay, x by x will give me x squared, so that is plus x squared. Nothing else. Why? Because the x squared here cannot be multiplied. We don't have constant term here. If we had constant term, yes, we have x squared, another x squared term, but we don't have any constant here. So x squared by any other term here will not give me x squared. So that's the only thing we have for powers of x squared. What about x cubed? Okay, we can multiply 1 by x cubed, so that will give me x cubed. So this is minus x cubed over 6, but that's not the whole thing we have here. X cubed can be gained also by multiplying x by x squared, but we don't have x squared here. Okay, we have x squared times x here, so it's plus x cubed over 2. Let us move. X cubed times anything here will not give me x cubed, so that's what we have, plus etc. That's enough, because we are looking only for the first 3 non-zero terms. So the answer will be x plus x squared. We have minus 1 over 6 plus 1 over 2, that is plus 1 over 3 x cubed. These are the first 3 non-zero terms in the Maclaurin series of the function. So clearly we can see now the constant term is 0. It's clear here. If you substitute 0, you have 1 times 0, which is equal to 0. So it's making sense here. So it seems that the second derivative divided by 2 factorial will be equal to 1. The third derivative divided by 3 factorial will be 1 over 3, and so on. So this is the idea of multiplying 2 power series. You just multiply, combine terms, similar terms together, and you get what we call the few terms of the Maclaurin series. Okay, the second part, let us say, about this idea here, which is multiplication and division, is how to perform division of power series. I will do a typical exercise here. Part B, I will do for tangent of x. Again, I repeat, we can do this power series representation by using the definition. I can go and evaluate the value of the function at 0, its derivative at 0, second derivative, third derivative, fourth derivative, and then find few terms. That's always possible. Alternatively, we can do this. I can rewrite the tangent of x as sine of x all over cosine of x. And what we will do here, we will do something like the long division, okay? In the long division of polynomials, we will do sort of that for power series. But instead of organizing the polynomial from the largest power to the least one, we will do the other way around now, from the least power to the, increasing powers, because here we have infinite series. So what is the representation of the sine function, for example? It is x minus x cubed over 3 factorial, that is 6, plus x to the 5 over 5 factorial, that is 120, minus etc. I'm interested only in the few terms, so 3 terms is enough here. What about cosine of x? Cosine of x is given by 1, what? Minus x squared over 2 factorial, that is 2, plus x to the power 4 over 4 factorial. 4 factorial is 4 by 3 by 2. 4 by 3 by 2, that is 24, minus etc. Okay? I divide like this now. What I will do, just take the first term, divide by the first term. X divided by 1, that is x. x by 1, x. X by x squared over 2, that is minus x cubed over 2, okay? X by x to the 4, that is plus x to the power 5 over 24, plus minus, I don't care about the rest, because I'm interested only in what? In a few terms of the series. So, like this. Now, what we need to do is to switch the signs first. So this is minus, plus, exactly of what we have done with polynomials, exactly the same. Adding, this will be 0. I have minus 1 over 6 plus 1 over 2, that is 1 over 3. So this is 1 over 3 x cubed, okay? And then I have 1 over 120, 1 over 120, x to the power 5, minus 1 over 24. If you multiply by 5, this will be 120, and that will be 5. So it is 1 minus 5, that is minus 4, over 120. So that is minus what? Minus 1 over, okay, 4 over 120. So this is minus 1 over 30 multiplied by x to the power 5 plus, etc. Next, I take the first term, divide by 1. So that gives plus 1 over 3 multiplied by x cubed. If you multiply back, what you have here is 1 over 3 x cubed, and then I have minus, and that is what? 1 over 6 x to the power 5 plus something that I don't care about, because I'm looking only for 3 terms. This will be enough to find 3 terms. Now I switch the signs. This is minus, this is plus, adding, this will be 0. I have 1 over 6 minus 1 over 30. Okay, if you multiply by 5, this will be 30, and this is 5. 5 over 30 minus 1 over 30, that is 4 over 30, or 2 over 15. X to the power 5. I'm just doing some, algebraic operations here, just adding rational numbers. So what is next? If I divide now, this will be plus 2 over 15, x to the power 5, plus, etc. Okay, no need to multiply because I'm looking only for the first 3 non-zero terms. It seems that tangent of x is given by x plus x cubed over 3, okay, plus 2 over 15 x to the power 5, and this will move like this. Of course, if you are interested in more terms, you need to add more terms here, you need to add more terms there, and then do the same way. That is simply the way we multiply 2 power series and to divide 2 power series. Okay. We will have now very nice result called the binomial series, which is a generalization of the binomial theorem we have, a plus b to the power n. Here we have, at that time we have for the binomial theorem, we have the exponent is positive integer. But now we will do it for a more general case, and that will be done in the following exercise. Now let us come and see now the generalization of the binomial theorem. Here we have something called the binomial series. What is the binomial series theorem? It says if k is any real number. Before we had this one as an integer, positive integer. Here we assume k to be any real number. So if k is any real number and absolute value of x is less than 1, then we have this. What does it mean? We have 1 plus x to the power k is equal to n equal to 0 up to infinity, k choose n, x to the power n, where we have, by definition, k choose 0 is equal to 1, and we define k choose n to be k times k minus 1 times up to k minus n plus 1 over n factorial. Before I use this one in an example, let me prove it for you. Let us see how to obtain this result here. If you look carefully for the theorem here, what do we have in the left hand side is 1 plus x to the power k. What do we have in the right hand side is its Maclaurin series representation. So what we need to do as the proof here, we will try to find the Maclaurin series of the function which is given by 1 plus x to the power k. That's exactly what we are looking for. We are looking for the power series representation or the Maclaurin series representation of that function. Okay, how to find the Maclaurin series representation of this function? Simply what I need to do is to find the nth derivative and evaluate at 0. That's exactly what we need to do. Okay? So what we need to do here, we need to just use the definition or the representation by Maclaurin. So this is n equal to 0 up to infinity. It says it's supposed to be if n at 0 divided by n factorial x to the power what? X to the power n. That's exactly what we have. That's exactly what we have. Okay. So let us find this. Find this, representation. So starting with the function f of x, you can see now this is 1 plus x to the power k, for k is an real number. This implies f of 0 is equal to 1. The evaluation of the function at 0 is equal to 1. Simply 1. Okay, what about the derivative of the function, f prime of x? The derivative of the function will give x times 1 plus x to the power k minus 1. And again, substituting by 0 in the derivative here, it will give this is 1, so this is equal to k. Fine. What is next? The second derivative. The second derivative of the function at x is equal to, it is k times k minus 1 times 1 plus x to the power k minus 2. So this implies the second derivative at 0 is k times k minus 1. Okay, let's do more so that we can see the generalization here. We'll do one more. If triple prime of x is equal to k times k minus 1 times k minus 2 times 1 plus x all to the power k minus 3. Fine. So what is the third derivative of this function at 0? Okay, the third derivative will be just k, okay, k minus 1 and k minus 2. So it seems that if we just differentiate this up to the nth order x, it seems, and we evaluate it at 0, what do we have? Okay, we will start with k, k minus 1, k minus 2. The question is where to stop. That's what we need to think about. Where to stop here. And if you just read these, derivatives we did, we can see now for the second derivative, we stopped at k minus 2 plus 1. Minus 2 plus 1, that's k minus 1. If you have a third derivative, then we stop at, this is k, k minus 1. What is this? It is k minus 3 plus 1. So it seems always we stop at k minus n plus 1. Let us check it and see. For example here, I need to start with k and stop at k minus 1 plus 1. So it's 0. So I need to stop at k, so it is only k. At the second derivative, I need to stop at k minus 2 plus 1. That's k minus 1. So I stop here. For the third one, it's k up to k minus 3 plus 1, k minus 2. So I will take only the first three terms and so on. So this seems to be the generalization of the nth derivative at 0. Substituting back in this formula here, we have 1 plus x to the power k is equal to summation now n equal to 0 up to infinity. And that is what? That is the nth derivative at 0, which is given by all of this product here. So it is k times k minus 1 times k minus 2 times k minus n plus 1 all over. Okay, we don't forget we have n factorial there. And this is x to the power n. Fine. What we do here is just to define this expression here. We define this to be equal to what? We define it to have the following simple here, up to infinity. That is k choose n, okay, x to the power n. And that is simply what we have. If you check the convergence here, that will be convergent if absolute value of x. This is the one. Again, that can be done by what we call the ratio test. This is now called the binomial series. Imagine now, if this k specifically is a positive integer. If it is a positive integer, so one time here, we have the difference is 0. For certain step here, for the calculation here, one of the coefficients, starting from one coefficient, everything will be 0. So this infinite series will degenerate to a polynomial stuff. So that is a special case now of the binomial series. Why it will degenerate to zero, to polynomial? Because you know, if you expand this, and k is an integer, n is running here. So one time, this n will be exactly equal to what? Equal to k. And then we just, we have the subtraction, k minus k, and that is 0. After which, everything else will be what? Will be 0 after that step. So we have some remarks of this, what we call binomial series. The first remark I have here, I have few remarks actually. Remarks about this result here we proved now. The first remark says, the first one, let's call it part A. It says the binomial series okay, this can be proved also that the binomial series is convergent also at x equal to 1, because here we have what? We have it between -1 and 1. We are sure this is convergent. At the boundary points, this remark says the binomial series is also convergent at x equal to 1 if we have k is between -1 and 0. For this specific choice for k, still the series is convergent at x equal to 1. This is one thing. The second one here, the second observation we can say about this, if we have k is non-negative real number greater than or equal to 0, the series is convergent, okay, not only between -1 and 1, but still it's convergent at 1 and at -1. So the series is convergent on this interval actually. It's -1 closed, 1 closed, okay? So that is if we mean by the binomial series convergent at 1, it means what we have is this. It's convergent actually is -1 up to 1 closed. That's what we mean, okay? So convergent at x equal to 1 means additional to the convergence here. So it is convergent on this series, in this interval, -1 to 1. So it is convergent on -1 to 1. If k is positive, non-negative, then it's convergent in the closed interval -1 to 1. That is the third remark I have here, which is the last one. If k is positive, if this k is positive, not only positive, it's not positive real number, positive integer. If it is positive integer, okay, if it is positive integer, then this implies that we have k over n is equal to 0 for all what? All n greater than k. Why? Because in one step it will pass through k minus k. K minus k will be 0. Multiplication will give me 0. So all terms after this will be zeros. And in this case, what do we have? The binomial series, is reduced to the what we call the very famous one, binomial theorem. That is, these are some remarks about the what we call binomial series. Now let us use this binomial series in finding the power series representation of a given function as an example. That will be done in the following exercise. Okay, it's the time now to see how to apply this binomial series to represent a given function in terms of Maclaurin series. So find the Maclaurin series of this function and state its radius of convergence. We will apply the binomial series. So the first thing we need to do is just to rewrite the function we have in this format, and that's exactly what we will do. I start with the function. So my f of x is written like this. I will just rewrite it as 4 minus x all to the power what? -1/2. Because we know the power here we said can be any real number. Okay. to put it in the form, I needed 1 plus something. So what I will do here, I will take the 4 common factor. So inside, I take the 4 common factor. What's remaining here is just 1 minus x over 4, all of this to the power minus 1/2. Fine, that's very interesting here. We have 4 to the power minus 1/2. That is actually 1/2. We take it outside. And then we have here 1, I will write it this way, 1 plus minus x over 4, all to the power minus 1/2. Now comparing this with the result we have, it's 1 plus x. So our x here is just minus x over 4. We need absolute value of this to be less than 1 for the convergence. So it means absolute value of x must be less than 4. So first of all, now the radius of convergence can be gained from here. That is, absolute value of x over 4 must be less than 1. So this implies absolute value of x is less than 4. So we have something about the radius of convergence. Okay, let us find the representation now. According to the theorem we have, this is equal to 1/2 times. Now, let's rewrite this in terms of summation. So it is summation. Now, go back to the binomial series. The binomial series says you start from 0 up to infinity, k choose n. What is k? K in that case is equal to minus 1/2, and x there is minus x over 4. Substituting, you have it n equal to 0 up to infinity. That is k choose n. Our k here is minus 1/2, so it is minus 1/2 choosing n what? We have x to the power n. What is our x here is minus x over 4. So it is minus x over 4 all to the power n. Again, I need absolute value of x to be less than 4. Fine. Let's write the final answer then. It will be just 1/2 times summation of n equal to 0 up to infinity. That is minus 1/2 choosing n. That is what? Minus 1 to the power n, x to the power n, all over 4 to the power n. I can write it as 2 to the power 2n, and then I can multiply by the 1/2 inside to get the following result here, n equal to 0 up to infinity. That is, if you like, minus 1/2 choose n, and then I have minus 1 to the power n, x to the power n, divided by 2 to the power 2n plus 1, and this is true if absolute value of x is less than 4. So that is one application for the binomial series, that if you are given a function that can be rewritten in this format, then we can find out what? We can find out its series representation with the definition of minus 1/2 choose n by the expression here. Minus 1/2 choose n, so you just substitute here minus 1/2, minus 1/2, minus 1, and then n is running over positive integers. That is what we call Maclaurin and Taylor series representations of given function. At the end, let me summarize what we have done for Maclaurin and Taylor series. Now you should remember now the basic functions we did. I will summarize them now. The basic functions we did for Maclaurin and Taylor series are the following functions. These are very important functions that we need to use them all the way when we discuss Maclaurin and Taylor series. You remember we did first 1 over 1 minus x. That is done by the geometric series test, and we can represent this one as a Maclaurin series to be n equal to 0 up to infinity of x to the n, and we said this makes sense if absolute value of x less than 1, meaning we have the radius of convergence is equal to 1. Simply, the radius of convergence is equal to 1. That is the first starting point. Then we succeeded by using, this is one. Second one, by using the derivative and integrals to find out the very beautiful here series tangent inverse that says it's equal to n equal to 0 up to infinity. And what we have here is minus 1 to the power n, x to the power 2n plus 1 divided by 2n plus 1. And we said here the radius of convergence again is equal to 1. And if you remember, we said also this is also convergent if x equal to 1, at x equal to minus 1. It can be proved it's still convergent. That is the second series we got, which is the tangent inverse. The third one we did today is e to the x. E to the x is n equal to 0 up to infinity. That is what? X to the power n over n factorial. And here the radius of convergence is infinite. It means it is convergent for any x. That is the third one. The fourth one, we derived for the sine of x in terms of Maclaurin series. This is equal to summation of n equal to 0 up to infinity minus 1 to the power n x to the power 2n plus 1 divided by 2n plus 1 factorial. Okay? And again, r here is just infinite. We just have the, it's true for between minus infinity and infinity, it's convergent. The fifth one, as a derivative of the sine, we did for the cosine of x. Cosine of x now, n equal to 0 up to infinity, we have minus 1 to the power n, x to the power 2n divided by 2n factorial. Okay? This is what we have. Again, the radius of convergence here is infinite. And finally, we did this, which is the binomial series, 1 plus x to the power k, where k is any real number. We said this is equal to the summation. Here we have n equal to 0 up to infinity. That is k, choose n, x to the power n, and we know that this is convergent with the radius of convergence is equal to 1. Okay, fine. We have to remember these formulas in order to apply them in different functions. So we get the benefit from these by substituting special points. For example, here, if you substitute 1, you will have a beautiful representation of pi over 4. If you substitute, for example, any point between, minus infinity to infinity, you have a different type of series where you can get what? Get the exact answer for the series by substituting a specific point in the left-hand side, the right-hand side. You have some beautiful results here. We use also this series to integrate some functions that are not elementary. We can also use them to find limits of some, different type of functions. We can also use them to represent other functions, like, for example, x cubed e to the x, e to the x squared sine of x cubed, and so on. That is simply what we call Maclaurin and Taylor series representation of functions. That's it.